But we're talking about hundreds of millions of times the mass of the sun. But it's a black hole, so it's small for that much mass.
Wow.
The sun goes around a black hole in the constellation Sagittarius at the center of the Milky Way galaxy.
However, the mass in question is hundreds of millions of times that of the sun. However, given its mass, it is small, a black hole. In the Milky Way galaxy's core, in the constellation Sagittarius, the sun revolves around a black hole. Researchers have found an astounding finding at the core of these mysterious cosmic monsters. They have discovered something horrifying and mind-blowing within a black hole, appending what we previously believed to be true about these celestial marvels. Get ready as we reveal the incredible mysteries that lie within the enigmatic center of a black hole. Do you want to learn more about it? Now let's get started. What a fascinating thing black holes are. Albert Einstein, a renowned physicist, said that even traveling at the speed of light would not be able to escape the strong surface gravity of his day due to his theory of general relativity. You are stuck here forever. Unlike pushing and pulling or magnetism, gravity is the outcome of mass and energy-driven objects curving or bending space and time. Envision possessing a gigantic object in space, akin to a star. The fabric of space and time surrounding it has a significant depression or bend because to its immense bulk and activity. We refer to this curve in space and time as the gravitational field. The object's gravitational field is greater and the dent it makes is deeper the more massive and energetic the item is. Now that theory is in place, let's discuss black holes. With unbelievable quantities of mass and energy condensed into such a small area, they are among the universe's most extreme things. Its massive mass causes its gravitational field to become extremely strong. The fabric of space and time is severely damaged by the powerful, deep dents caused by this high gravity. This is where things get very weird. An event horizon is formed when the gravitational attraction of a black hole gets so intense that it approaches the black hole. The event horizon is just space passing through without obstruction. It is not a wall. A point of no return or invisible limit is what it feels like to cross the event horizon. Anything that crosses this line, be it light or an unfortunate spacecraft, can never again escape the black hole's clutches. It appears as though everything, even light, which is typically the fastest object in the cosmos, is contained inside the black hole by an unseen force field. To put into perspective just how amazing this is, picture yourself holding a flashlight. The laser beams move at a speed of over 300,000 kilometers per second. The speed you would need to escape a black hole, however, would be much quicker than the speed of light if you were within one. As far as we now understand physics, that is not feasible. Thus, light that falls into a black hole becomes stuck there forever and cannot escape. Light from a greater distance is curved around it. Thus, we must not overlook the event horizon, a mysterious boundary, when discussing black holes. It resembles a point beyond which anything courageous or unfortunate enough to cross it cannot return. Something can never return once it passes through that point and plunges into a black hole. The event horizon is a mathematical term that indicates the point at which we can no longer perceive what is happening. It is not something you can physically touch or see. One may question what the size of this event horizon is. All of this is dependent upon the black hole's mass, or the Schwarzschild radius. A black hole's event horizon will enlarge with increasing mass. The Schwarzschild radius is the value that scientists have determined to be the event horizon's radius. It was discovered in 1916 by an astronomer by the name of Carl Schwarzschild. The Schwarzschild radius is calculated by dividing the black hole's mass by a formula that takes into account both the speed of light and the gravitational constant. For instance, the event horizon of a black hole with a mass 10 times that of the Sun would be around 30 kilometers in radius. An entity called the singularity is located in the center of a black hole. No matter how enormous, everything of the black hole's mass and energy are crushed and squished into an indefinitely small, dense point at its core. This point is known as the singularity. It resembles a cosmic heavyweight with amazing curve and gravity. It's actually rather amazing that the singularity has limitless curvature and unlimited gravity. The problem lies in the fact that, while attempting to explain what occurs at the singularity, our knowledge of physics begins to break down. We just aren't aware of what occurs there. We are left wondering why the rules that govern our cosmos seem to take a pause or go on vacation. Researchers continue to go into this mysterious area in the hopes of learning the mysteries that lie at the center of black holes. Furthermore, how do black holes form? You know, everything begins with a huge star's life cycle. Deep within their cores, these stars undergo remarkable nuclear fusion events that drive them like celestial powerhouses. Think of these responses as an amazing culinary program. Fusion is a particular nuclear process that converts hydrogen into helium, which fuels the sun. When two hydrogen atoms are forced together, one helium atom is produced as the byproduct, where a huge quantity of energy is released as hydrogen atoms combine to generate helium atoms. Now, the star stays stable as long as it has enough hydrogen fuel to continue the fusion process. However, celebrities are avaricious and desire to prolong the fusion celebration. They become a little inventive when the hydrogen in their core runs out. They begin combining elements that are heavier, such as oxygen, carbon, and helium. Less energy is produced by each heavier element fusion process than by the preceding one. The star must burn hotter and work more to make up for this, increasing the heat in order to preserve its delicate equilibrium. Sadly, the voyage of every star must come to an end. The star approaches a point of no return when it is unable to combine additional elements. Something amazing is happening right now. A black hole is created when the star's core collapses due to its immense weight, like a beautiful implosion. The singularity, the center of the black hole, that we previously discussed is formed when the core collapses. Not even light can escape the strong gravitational attraction created by this singularity, which contains all of the star's mass and energy in a little amount of space. It has the effect of drawing everything into its gravitational pull like a cosmic vacuum cleaner. What happens to a star when its life is about to end relies on its mass, or, more accurately, on its size. Let's divide it into three outstanding weight groups. First up are stars with a mass less than 3 times that of the Sun. These stars are about to undergo a change. Rather than ending dramatically, they transform into an entity known as a white dwarf. It's as if the celebrity decides to gently step down. Inside is a compact ball of carbon and oxygen atoms that is still emitting light in the form of leftover heat. Now, prepare for an amazing show if the star has a mass of anywhere from 3 to 20 times that of the Sun. These stars explode with a tremendous supernova explosion. This star's core collapses dramatically in the middle of the explosion's mayhem. It turns into a neutron star, which is a very dense ball. Imagine packing a small sphere with a radius of just around 10 kilometers, containing up to double the mass of our Sun. Now, actual heavyweight stars, those that are heavier than around 20 times the mass of the Sun, explode in a supernova similarly to their somewhat lighter siblings. But the fate of these massive stars' cores is different. Under the force of its own gravity, it falls, but it doesn't end there. Once more, a black hole is created when the gravity gets so strong that the center contracts to zero volume and infinite density. There are several varieties of black holes. We have black holes with stellar masses. These originate from huge stars that are getting close to the conclusion of their stellar journeys. They are usually a few times to several tens of times as massive as our reliable Sunday. In reality, both our galaxy and other galaxies throughout the expanse of space are home to a large number of stellar mass black holes. Let's now turn our attention to the gigantic supermassive black holes. The real giants of the black hole family are these enormous cosmic entities. Their masses are millions, if not billions, of times larger than the Sun's. Imagine them as the lords ruling over most massive galaxies, like the Milky Way, from their central position. These enormous black holes are believed to have originated in the early phases of the cosmos as a result of smaller black holes merging or vast gas and dust clouds collapsing. Their existence has a significant impact on how galaxies evolve, influencing how stars and planets that orbit them originate. Well, we have now encountered intermediate mass black holes, an uncommon kind. In terms of mass, these enigmatic entities fall in between stellar mass and supermassive forms. They are quite enigmatic and seldom seen, much like the middle offspring of the black hole family. Although their exact origin is still unknown, scientists believe that they might have arisen from the merger of stellar mass black holes in densely populated star clusters or from the collapse of extremely massive stars in the early cosmic periods. And then, there are the fascinating primeval black holes. These might be remnants from the first moments of the cosmos, created not long after the Big Bang. They are born because of variations in matter and energy densities in those early cosmic moments. There are many different sizes of primordial black holes, ranging from tiny ones with weights of only a few grams to gigantic ones thousands of times heavier. Then the Sun. Remember that although primordial black holes are an intriguing concept, they are still theoretical and have not been witnessed firsthand. Rotation is another fascinating feature of black holes. The Schwarzschild black holes are one example. These are the easy ones, the ones that don't spin. Consider them the group's cool, collected black holes. The Schwarzschild solution, a mathematical explanation found in Einstein's General Theory of Relativity, describes them. These black holes feature a unique point in the center known as the singularity and a lovely, spherical event horizon, which functions similarly to a border denoting the point of no return. It resembles a single dot with a powerful gravitational attraction. Similar to this, you will reach the center if you fall through a black hole's event horizon. Next, there exist Kerr black holes, which the general relativity Kerr solution describes. Their event horizon is flattening or becoming oblate due to their rotation. In a Kerr black hole, the singularity has a ring-like form. The ergosphere is created when a rotating Kerr black hole rotates. The area surrounding the black hole resembles a cosmic vortex as the spinning black hole drags space and time with it. Let us introduce you to the Kerr-Newman black holes. These are the rotating rock stars with a little something extra. They have an electric charge in addition to spinning. In general relativity, Kerr-Newman black holes are characterized by the Kerr-Newman solution. Their ring-shaped singularity and oblate event horizon are two features they have in common with Kerr black holes. But the electric charge gives their tail a new angle. The electric field somewhat distorts the event horizon and singularity. Ultramassive black holes have also been discovered by scientists. Extremely big black holes are amazing cosmic heavyweights. At almost a staggering 10 billion times the mass of our dependable Sun, it tops the scales. We are discussing a black hole with an unfathomably powerful gravitational attraction. Anything that approaches it too closely is going to go through a crazy roller coaster. How in the world did we find these cosmic monsters? An astute group of astronomers from Durham University in the United Kingdom accepted the challenge. They employed a state-of-the-art method known as gravitational lensing. It may sound elegant, but it's genuinely quite interesting. The amazing general theory of relativity developed by Albert Einstein states that large objects, like as galaxy clusters, have the ability to bend and warp the course of light. This gravitational lensing method allowed the researchers to identify the distinctive features of an ultramassive black hole. In my opinion, we may be witnessing the emergence of new laws of physics due to the massive black holes that we are studying. They saw the amazing light bending and magnifying that this cosmic heavyweight produced. In addition to proving the existence of ultramassive black holes, this important finding offered more evidence in favor of Einstein's general theory of relativity. The powerful Hubble Space Telescope was used to make this finding. Our daring researchers focused on the AEL 1201 galaxy cluster, which is located 2.7 billion light-years from Earth. This is where things start to get really interesting. Looking into space, they saw something strange, a massive arc of light around the cluster. But that arc was more than just a regular light display, it was the warped representation of a distant galaxy, stretched and smeared by the cluster's gravitational pull. And how, then, did they solve this cosmic riddle? They used the computing capacity of supercomputers, after all, to model the motion of light across the enormous cosmos. They were able to determine the mass and position of the object, causing the lensing effect by meticulously recreating the background galaxy's brightness and shape. And you know what they found? A supermassive black hole was discovered to be hiding in the center of one of the cluster's galaxies. The mass of this black hole was an incredible 30 billion times that of our own Sunday. That's among the biggest black holes in the cosmos that has ever been seen. Moreover, this amazing finding was the first instance of a black hole being identified through the use of gravitational lensing. The remarkable power of gravitational lensing is highlighted by this discovery. It's like having a cosmic magnifying glass that lets us view and learn about things that would otherwise be too faint or concealed to be directly detected. By using this method, there are a plethora of new opportunities to solve the riddles surrounding black holes and other unusual objects that may be hiding deep within space. Consequences: for example, if you observe gravitational lensing in action, you may utilize what you observe to calculate the mass of the lens. This brings up an incredible application of the gravitational lensing theory. It allows us to see the invisible. However, this extremely huge black hole throws a wrench into our understanding of how they formed and expanded in the early universe. You see, the conventional theory of how black holes form over time is called into question by its sheer magnitude, which is so very huge. It would have required an incredible rate of accretion to attain such a massive mass, 30 billion times that of our Sun, in just 13 billion years after the Big Bang. Imagine it as an accelerated feeding frenzy that draws matter in at a startling rate. Alternatively, it might have created via spectacular mergers in which it collided with other black holes in the universe. This finding provides new and fascinating opportunities to explore the cosmic processes that formed these mysterious cosmic giants. Nevertheless, we have a unique chance to test Einstein's theory of relativity in harsh environments because to this extraordinary ultramassive black hole. Test, by examining these cosmic monsters that defy our comprehension of gravity, we may test if Einstein's hypothesis still holds true in the most extreme cosmic conditions. It is akin to carrying out an intergalactic investigation that explores the fundamental structure of space and time. Finally, this finding presents an enticing opportunity to investigate the characteristics and nature of dark matter. The bulk of the material in our universe is made up of dark matter, an enigmatic and unseen kind of substance. We can learn more about the distribution and impact of dark matter and its elusive nature by examining the behavior and interactions of ultramassive black holes such as this one. When mass, space, and time come together, gravitational lensing produces amazing visual illusions akin to a cosmic magic show. This is how it works. Mass has a significant impact on the structure of space and time, causing it to twist or curve around itself, in accordance with Einstein's theory of relativity. Imagine it as a trampoline with a divot caused by mass. This warping causes objects passing close to follow bent pathways. Now, this cosmic phenomena also applies to light, which generally moves in straight lines. The gravitational warp catches up with light when it passes through enormous objects like galaxies or clusters of galaxies, causing it to follow curved pathways as well. Herein lies the significance of gravitational lensing. Consider that there is a light source in the backdrop, such as a star or a far-off galaxy. Its light encounters a large object along the way that serves as a cosmic lens as it makes its way across the cosmos towards us. The light from the background source is bent, magnified, or otherwise deformed by this enormous object due to its strong gravitational attraction, producing captivating effects. Gravitational lensing comes in a variety of forms, each with unique peculiarities. First, let us consider weak lensing. The forms and locations of faraway galaxies are subtly altered. It's like wearing slightly hazy glasses. It will need statistical analysis of several galaxies for scientists to find these alterations. Important information on the distribution and amount of dark matter in massive cosmic structures such as galaxy clusters may be obtained via weak lensing. It's similar to finding unseen cosmic fingerprints left by the enigmatic dark matter, and this brings us to an incredible application of gravitational lensing theory. It allows us to view the invisible. Let's go to stronger lensing now. This is analogous to a cosmic superpower that materializes when a huge item and a far-off source perfectly coincide. Multi-images, arcs, circles, or other distorted patterns of the background source whirling around the lensing item are examples of the mind-bending effects that may be produced by strong lensing. It resembles peering through a kaleidoscope of the cosmos. This strong phenomena not only magnifies and reveals hidden features of distant sources that would otherwise be too weak or tiny to view, but it also aids in the measurement of the mass and form of the lensing item. Then, there is a unique situation known as microlensing, which adds a hint of heavenly drama. When a smaller object, such as a planet or star, passes directly in front of a more distant star, microlensing occurs. The background star seems larger or brighter as it becomes lensed because the foreground object serves as a temporary magnifying lens. Microlensing is an interesting technique for identifying other rare cosmic wonders, such as black holes or neutron stars, as well as planets orbiting other stars. Scientists have targeted their advanced telescopes on a supermassive black hole located 800 million light-years distant, near the center of a galaxy, and they have discovered something startling inside a black hole for the first time ever. Black holes are notorious to eat everything that approaches them too closely, owing to their voracious appetites. Well, in this instance, something remarkable was brought about by the black hole's cosmic feast. Gas from the surrounding area was heated to extremely high temperatures, millions of degrees, when it plummeted into the black hole. Like a bright cosmic halo, this scorching hot plasma created a luminous corona surrounding the black hole. The crazy thing is that these X-ray flares, cosmic fireworks, produced by the superheated gas, didn't simply vanish into the cosmic abyss that is the black hole. Whoa, they did have a cosmic rebound after all. The X-ray flares were able to escape, but in an unusual way, the gas just behind the black hole reflected them. That's not all, though. These reflected X-ray bursts then encountered another cosmic barrier, the black hole's magnetic fields and mind-bending gravitational force, as if defying the rules of physics.
Hey there, friends. In 2014, Christopher Nolan directed a movie called Interstellar that became a huge hit. Space ideas like wormholes, black holes, and alien worlds were shown in this movie in a way that was true to science. The most shocking scene, though, may have been at the end of the movie. There is a moment in the movie where Cooper, the main character, falls into a black hole. The movie's black hole was called Gargantua. He and his spaceship fall into the black hole. At first, there was nothing but darkness all around him, but as he sinks further, he sees what look like grains. These particles hit his spaceship and scratch it up. There were sparks and flashes of light, and then his spaceship caught fire. As he fell into the black hole, he had to be thrown out of his spaceship. All of a sudden, he was in a space with 5 dimensions, a tesseract with 5 dimensions. It was a very strange event, a place where, by using gravity, he could talk to his past self. When you saw these scenes, you might have thought, is that really possible? Is this real in a black hole? What will we see if we go into a black hole? Let's try to understand these things in today's video.
Black holes remained largely unknown until the 20th century. A black hole is a region in space where the force of gravity is so strong, not even light can escape.
From the outside, you can't tell what is inside a black hole.
Black holes haunt our universe, dark centers of gravity that swallow everything in their path.
Friends, let's start with the beginning of this story. Black holes have only been around for a short time. People didn't know about black holes 100 years ago. Black holes were later found thanks to Einstein's theory of relativity. Friends, the idea is made up of 2 parts. There is the General Theory of Relativity and the Special Theory of Relativity. Einstein wrote the Special Theory of Relativity in 1905. It explains how speed changes the passage of time. If you are in a rocket going too fast, time will slow down for you, in terms of the people on Earth who are not on the spaceship. To be clear, the word relative is very important, because time would not seem to slow down in space. Since everything looks the same, time seems to be moving at the normal speed. But when you get back to Earth, you'll see that time moved differently. Kinematic time dilation is the name for this. I also went into a lot of depth about how this works in my movie about the time traveler. Einstein's General Theory of Relativity shows that time can be slowed down by things like speed and even gravity. He came up with this idea in 1915. For you, time would move more slowly the more gravitational force you felt. As a result of gravity, time seems to stretch out. And Interstellar did a great job of showing this. The Aqua planet is 7 times bigger than Earth, so 1 hour there is equal to 7 years on Earth. Things like this happen on the planet because it was really close to the Gargantua black hole. In other words, the black hole's gravity pull changed the time. Einstein wanted us to picture a space-time mesh to help us understand this. Like a mesh, all the things on the world are placed on it. Space-time bends because of how heavy the things are. When the mesh bends, it not only pulls real things toward it more strongly, but it also slows down time. Other types of energy, like sound, heat, and light, are also affected by gravity. Yes, that is true. This is another thing Einstein came to the conclusion of. Almost everything is affected by gravity. The force of gravity pulls not only solid things toward it, but also sound, light, and heat. Friends, this means that there may be things in the universe with such strong gravity pull that they can soak up all light. That means that if there are such things, they would be totally black. They won't be visible to us. They are so strong that not even light can get through. You guessed it, this is what black holes are. Black holes, on the other hand, were just ideas when Einstein introduced his theory of general relativity. Einstein knew that light is affected by gravity, and it was possible in theory for things to be able to receive light. Einstein didn't know there were black holes, though. Einstein himself thought the idea of black holes was strange when he was living. In theory, he knew that things like that could exist. But in theory, it's also possible for there to be no end. But he didn't really believe that things like that existed in the real world. By the time he died, no one had even thought of the word black holes. As a fun fact, Einstein's theory was based on the idea that gravity can only affect things that are moving faster than light. Gravity's strongest force is the speed of light, so we don't feel it all the time and everywhere. As an example, let's say the sun went away all of a sudden. As you know, we'll find out about it 8 minutes later on Earth, since it takes 8 minutes for sunlight to reach Earth. Einstein said that the sun's departure would also have an effect on the Earth 8 minutes later. Isn't it fascinating? After Einstein, many scientists worked on the theory of general relativity. It was made up of a bunch of equations that had to be solved in order to find their solutions. Once they did, it was thought to be theoretically proven that things like black holes do exist. For the first time, experts and scientists finally agreed in the 1960s that we would be able to see black holes in real life one day. There are things like these in space. In 1964, a magazine was the first to use the phrase black hole. But it wasn't until scientist John Wheeler made the term famous after 1967 that it really took off. The name black hole is not what it seems to be, even though it sounds exciting. Black hole, it sounds like there might be a hole there. That's not true, though. The place doesn't have a hole. Stars make black holes. That means there is something in the middle. In the stars, though, our sun is a star, there is a nuclear fusion process going on all the time. Light and heat are made by these processes. A force is sent outward by the heat being made, and there is a force of gravity at the center of the star that helps it stay living and whole. Stars stay in balance all their lives by having forces pushing outwards from the reaction and forces pulling inwards from gravity. But these processes can only happen if there is fuel. It could be hydrogen or helium. There wouldn't always be power. At some point, it would catch fire. When the fuel runs out, there won't be any forces pushing outward, and the force pulling in from the outside wouldn't be balanced by a force of the same size, so the star will fall apart naturally. Also, this will take a long time. The sun is thought to last about 10 billion years, but the next thing that happens will depend on how heavy the star is. Take a look at the picture that shows how a star changes over time. It turns into a red giant if the star's mass isn't very high, which means it was a small or average-sized star. It can then turn into a white dwarf or a planetary cloud. But if it was a big star, it would cool down and turn into a red supergiant when it ran out of fuel. The supergiant then explodes and changes into a supernova. After this, only a small core is left. A neutron star is a small core, but a black hole is anything bigger. When a star's gravitational pull causes it to shrink, its mass gets very small and concentrated. It can then turn into a black hole. To be more specific, how small is the star's volume? If a star as big as our sun turns into a black hole, it will only be 50 kilometers across in diameter. Could you picture the amount getting this small? The interesting thing is that our sun won't turn into a black hole. An Indian-American astronomer named Subrahmanyan Chandrasekhar proved this. The Chandrasekhar limit number was made by him. He said that a white dwarf could have as much mass as 1.4 times the sun. It would either become a neutron star or a black hole above that point. But since the sun, our sun, is below this limit, let's look at what a black hole is. Friends, black holes come in 3 or 4 main types. Star black hole is the first one. There are a lot of these kinds of black holes. These are the black holes that stars made. They think that there are between 10 million and 1 billion of these black holes in our galaxy, the Milky Way. And then there are the first black holes. A black hole is about the size of an atom, but they have the weight of a rock. They are thought to be about the size of an atom. Dear friends, these black holes are just ideas. We don't really know much about them. The supermassive black hole is the third kind of black hole. These black holes are very big. It's so big that it weighs more than 1,000,000 suns put together. It also fits into a ball that is as big around as our solar system. It is thought by scientists that there is a supermassive black hole at the center of every big star. Sagittarius A is the name of the enormous black hole at the center of our galaxy, the Milky Way. Gargantua was the name of the black hole in the movie Interstellar. Plus, experts think there might be a fourth kind of black hole as well. There is a chance that the fourth type of black hole will be an intermediate black hole. These are black holes that are between the sizes of stellar black holes and supermassive black holes. But so far, no proof of it has been found. The black hole is not like a big black ball that sucks everything around it, as you saw in the movie Interstellar, and in the pictures you've seen so far and how you understand them. This is kind of how the black holes look. We know this is the black hole from the movie because it is in HD and has more depth than the picture we took a while ago. The orange ring that forms around the black hole is the first thing that you'd notice in this picture. The accretion disk is its name. This is a very important thing about black holes. As you know, black holes have very strong gravity pulls. Because of these pulls, a lot of gaseous matter and waste is drawn to the black hole and stays floating around it, along the same lines as how planets orbit around the sun because of its gravity. What makes black holes different is that their gravity is so strong that anything spinning around them goes very fast and gets so hot that the matter turns into a fluid-like substance. They turn into particles that look like fire and are hotter than 1,000,000 degrees Celsius. They are going around the black hole faster as they get closer. Because the particles are spinning so fast, they rub against each other and get squashed, which makes them glow. They give off electromagnetic waves, most of which are X-rays. The movie did a great job of showing this accretion disk. The only thing they got wrong was that it isn't orange. We can't see X-rays with our eyes. X-rays are not in the range of light that humans can see. We just call it an orange-yellow color to make it easy to understand. This disk is more likely to be blue in real life. The first picture of a black hole was taken in 2019. The accretion ring was still shown in this, with a yellowish-orange color. In the picture, the particles on one side are lighter than the particles on the other side, which you might not notice in the movie. That's because of a simple thing. The particles that are moving toward us look brighter than the ones that are moving away from us. This is because of the Doppler effect. Before you see the real picture of this black hole, you can look at this fuzzy picture and figure out which way the particles are moving. The brighter area is moving toward us, while the darker area is moving away from us. Looking back at the movie picture, another cool thing you might notice is that the accretion circle creates a trick of the eye because of gravity. The disk seems to cover both the top and bottom of the black hole. This is how it looks because of how gravity bends light. When looked at from the front, the area behind the disk is covered. The light that comes from that area has to move over it because gravity bends it. From above, the black hole will look like a normal, round disk. We can only see this effect when we look at the black hole from the sides. Besides this, there will be one last circle of light when you go into the black hole. It is called the photon sphere. This place has such strong gravity that light starts to circle the black hole. What does light come from? Photons. The photons begin to circle the black hole. So if you make it to this part of a black hole while you're still living, you might be able to see the back of your own head because the light is moving in a circle. The edge of the black hole is after this point. The event horizon is the name for this. People call it a barrier because gravity is so strong after this point that not even light can get away. After this point, everything is black. If you've already crossed the event horizon and are falling into a black hole, there's no way you can get out. If light can't get away from it, how could a person? In the movie Interstellar, Cooper's spaceship keeps going into a black hole, goes past this event horizon, and then all of a sudden he is in a place with 5 dimensions. This scene from the movie is just made up. We don't know what's inside the event horizon, so this is just a guess. A Nobel Prize-winning scientist was chosen by the people who made Interstellar to make sure that everything was scientifically correct. But it was clear that the movie turned to the fantasy for parts that were about things that science hasn't found yet, or that we don't know anything about. What will be in the black hole's middle? A theory by Einstein called the General Theory of Relativity tries to explain this. Singularity is the word for the center of this black hole idea. In the center of a black hole, where the singularity is, the curve of space-time is infinite. Remember the mesh I talked about at the beginning of the video? The space-time mesh will bend more when something is heavy. In the case of a black hole, this is bent so far that it goes on forever. As we know from the theory of relativity, gravity changes everything, including time. As the gravitational force rises, time keeps getting slower and slower. What does it mean, though, for time to slow down forever? Does this mean that if you go into a black hole and then manage to get out, the world outside would have finished for everyone else? We don't know. We can only think of ideas. What do you think? Say something below and let me know. People have come up with some interesting ideas. Light is swallowed by a black hole, so we can't see inside it from the outside. According to one idea, light bounces off of the event horizon several times before it reaches the singularity. So it's possible that things would be able to be seen inside the event horizon. This picture is the only thing we know for sure about black holes. This picture was taken on April 10th, 2019 by the Event Horizon camera. This pretty much showed that black holes exist, about 100 years after they were shown to be true in theory. One thing is for sure, if you fall into a black hole, the gravity pull will likely break you up into a million pieces. You're going to die in a second. Still, friends, you don't need to be afraid of black holes. A long time ago, a lot of people thought that black holes ate all the matter in the universe, kept getting bigger, and finally wiped out the whole thing. That's not how it works, though. As I said, there is an enormous black hole at the center of every star, and all the planets and stars that are close to the black hole move around it. This is like how all the planets in our solar system move around the sun. At the center of the world, the same thing takes place, but it's much stronger. In conclusion, you will be safe and sound if you keep your distance from a black hole or if you keep your distance from other people. The idea of 5 dimensions, which was talked about in Interstellar, is also an interesting one. In another movie, let's talk about it. That's all for now. If you like this video, you can see more about space. If you haven't already, watch the video about time travel. There, these ideas are explained in more depth.
Among the most intriguing and enigmatic things in the known cosmos are black holes. They are a formidable force because they have the ability to warp spacetime and an insatiable hunger for substance. For many years, researchers have been studying black holes, but until recently, they have been unable to obtain any tangible data. The sharpest image of a black hole ever seen has now been made public by scientists. Come along as we explore the realm of black holes in greater detail and discover the significance of this picture, which has the potential to alter our understanding of them forever. But let's pause for a moment before we do that. Black holes weren't exactly simple to locate. Philosophers and scientists have been perplexed by the nature of the cosmos and the enigmatic forces that sustain it for ages. The discovery of black holes was a significant turning point in humanity's quest to learn the secrets of the cosmos, which dates back to ancient civilizations. Back in 1783, a sharp thinker made a daring forecast that set the whole thing in motion. John Michell, an English natural philosopher, proposed a theory that suggests there might be massively powerful, unseen objects in space that could be identified by observing a star's orbit. Following the publication of the theory of production in 1916, Albert Einstein's General Theory of Relativity established the foundation for contemporary theories of gravity and spacetime structure. According to Einstein's theory, large things have the potential to deform and twist spacetime around them. The Newtonian theory of gravity as a solely attractive force between objects was challenged by this groundbreaking idea. Numerous things, including the potential existence of black holes, were affected by Einstein's hypothesis of how objects behaved in the cosmos. It is believed that enormous stars that are nearing the end of their life collapse to generate black holes, which are extraordinarily large phenomena. Consider it this way: a star that runs out of fuel is unable to provide the necessary pressure to resist the pull of gravity inward. When a star reaches a sufficiently large mass, its core will simply collapse due to gravity, leaving behind a black hole in the place of the former star. Okay, so all of this makes sense now, but nobody was interested in considering the possibility of black holes in the past. For several years, black holes remained completely theoretical, despite the fact Einstein had already predicted their existence. Some scientists thought the concept was ludicrous, while others thought it was too fantastical to be true. In the 1970s, astronomers Paul Merton, Thomas Bolton, and Louise Webster made the observation that an unseen object was 6,000 light-years distant, circling a blue star. It turned out that the object, codenamed Cygnus X1, was the first black hole ever discovered. About 6,000 light-years away from Earth, in the constellation Cygnus, lies a binary star system known as Cygnus X1. A large blue supergiant star and a compact object, possibly a black hole, make up the system. Astronomers noticed that the system was producing X-rays in the late 1960s. X-rays are very powerful electromagnetic radiation waves that are usually connected to extreme cosmic phenomena like supernova explosions and the acceleration of mass onto black holes. The fact that the X-rays were coming from a nearby source that was completely invisible to optical telescopes, meaning it was practically difficult to capture an image of one on camera rather than the blue star itself, perplexed the scientists researching Cygnus X1. Researchers speculated that material from the outer layers of the blue star may be being ingested by the black hole. Telescopes can detect the X-rays that are released as matter falls towards a black hole because they are extremely hot. That's what they began investigating instead. Cygnus X1's discovery was a significant advance in the hunt for black holes, as it offered verifiable proof of their existence and unlocked a completely new field of study. It also proved that contemporary astronomy is capable of delving into the greatest secrets of the cosmos and supported Einstein's theory of relativity. Although it is impossible to directly view black holes, their influence on the surrounding material may be noticed. For instance, a star orbiting a black hole experiences a Doppler shift in its light as a result of the star's increasing speed due to the black hole's gravity. The black hole's mass may be determined by measuring this shift. The detection of black holes can also be accomplished using gravitational lensing. The gravitational attraction of a black hole causes light from far-off objects to be bent and twist around it when it approaches. A distorted picture of the item may result from this phenomenon, which may be seen and utilized to verify if a black hole is there. There is still a great deal we don't know about black holes, despite the abundance of knowledge we have previously amassed. Even more absurd is the fact that they are present everywhere, not only in the universe's shadows. Supermassive black holes are found in the cores of at least 2 trillion galaxies in the visible universe, and there may be as many as 400 million of them in our own Milky Way. We had merely not noticed them, but they had always been there, everywhere. Similar to the bullies of the cosmos, black holes swallow everything whole and never let it go. For this reason, expanding our knowledge about black holes is crucial. Anything that steps too close will be engulfed, reduced to a single particle, and ultimately rendered insignificant. The fact that every black hole is different, with its own gravitational pull and set of laws, is what makes them all the more dangerous. It is possible for one black hole to behave exactly like another. A black hole is composed of 3 layers: the singularity, the inner and outer event horizons, and the outer layer. The point from which you can never return is known as the event horizon. It is the line encircling the black hole's mouth. In most cases, the moment something reaches the event horizon, it's finished. Similar to being stuck in quicksand, the more you try, the more you sink. However, in this instance, the quicksand is the black hole's gravity, and there is no way out. You will be drawn further into the black hole to the inner layer if, by some miracle, you are able to cross the event horizon. Inside a black hole, the known rules of physics do not hold true. There, it seems like a completely separate cosmos. Space and time are bent by the force of gravity, which is so great that everything is compacted to a single, tiny point known as the singularity. The black hole's singularity, where the majority of its mass is concentrated, is its core. It is a point with zero volume and infinite density. Don't be fooled by this, though. Light cannot escape the singularity due to its intense gravitational force. Because they don't release any light, black holes get their name. As a result, they completely destroy anything they come into contact with. Although they have a frightening reputation, black holes are interesting objects. So how exactly do scientists investigate these celestial monsters? They investigate the radiation that black holes release as well as the gas and particles that surround them. It is comparable to analyzing an out-of-focus snapshot of a far-off item. There's a limit to how close you can get before your camera vanishes into thin air, something you definitely don't want. How then do scientists interpret all of this? Of course, they have a ton of hypotheses. To put it mildly, the answer to the issue of what lies beyond the event horizon that scientists have been posing may surprise you. What if there was a gate there, a portal to another universe, galaxy, or even dimension, rather than just nothingness? Now, this is no ordinary gate that we are discussing. We are discussing a technology that would enable us to travel faster than light, which is presently believed to be unachievable. However, if we could somehow develop the technology to do so, we could be able to travel into a black hole and come out into a whole different universe. Though it may sound absurd, it's not as unfeasible as it first appeared. According to certain hypotheses, the singularity at the center of a black hole might be a wormhole leading to another galaxy. Think of the possibilities. A black hole, a flaw in the matrix, may allow us to visit far-off stars and discover new worlds. Naturally, that's a long way from being a reality. Regarding black holes and the nature of space and time, there is still much that we do not know. It's astounding, though, that we're even thinking about the possibility of employing black holes as a shortcut for interplanetary travel. Furthermore, if this notion is true, it may completely alter the landscape of space exploration. Still, not all scientists believe that this is feasible. Some believe the solution is much more straightforward yet still somewhat complex. How about if black holes were just illusions? Tokyo-based scientist Enrico Rinaldi thinks just that. According to his holographic duality hypothesis, we should view black holes as holograms in order to fully comprehend them. This implies that we should investigate the external events around the singularity rather than the inside ones. Nevertheless, how is a black hole a hologram? Well, gravity and particles are the main players in this. Black holes function in the third dimension, according to Rinaldi and his colleagues, and their surroundings are a component of the equation. In fact, the gases and dust particles that whirl around a black hole provide details about its nature. Consider a black hole as a ring that is gradually devouring everything in its path rather than as a sink. It gets stronger and draws in more particles and gases as it takes in more and more stuff. This produces an energy vortex that spins and is visible for light years. What does this imply for our knowledge of black holes, then? It implies, among other things, that we should turn our attention from the singularity to the area surrounding it. We may learn more about black holes' capabilities and modes of operation by examining the patterns of gases and particles. However, this theory's consequences reach beyond black holes. Holographic duality has the power to alter our conception of the cosmos as a whole. It implies that what we perceive as real could actually be a hologram or projection of something else. Though it seems like something from a science fiction film, this is actually a possibility. This hypothesis states that our perception of three dimensions is really only a projection of a two-dimensional surface. Though it may appear counterintuitive, this idea is grounded in science. A well-known physics theory called the holographic principle postulates that data in one area of space may be represented by data on another area's surface. Stated otherwise, a space's content can be projected onto its edges, resulting in a structure like to a hologram. The holographic principle has the potential to completely transform our conception of the cosmos. It could imply that what we understand about the universe is really a projection, a shadow of something greater. However, what else might that be? According to some scientists, there could be several holographic projections reflecting distinct realities, and our world might just be one of them. This might imply that there are a vast number of parallel worlds, each marginally distinct from our own. Furthermore, if the theory that black holes are portals is correct, they could hold the secret to knowing everything. Hey, they are all still only speculations. The real understanding of things makes all the difference. For ages, scientists have conjectured about these unseen behemoths of space. We now have a breathtaking image of one at the heart of our own Milky Way galaxy, courtesy to the visionary work of the Event Horizon Telescope (EHT) group. The supermassive black hole at the center of our galaxy is called Sagittarius A. Given the evidence of stars orbiting something unseen, compact, and incredibly massive, scientists have long hypothesized that this mysterious object was a black hole. However, the picture they took offers the first concrete proof of it. It's difficult to accept that what we're seeing is a black hole since the visual is so beautiful in and of itself. The black hole itself is absolutely dark, so we cannot see it, but its blazing environs show us its unmistakable signature, a dazzling ring-like structure around a dark center area. The black hole's tremendous gravity has actually twisted light into this ring. It is an astounding 4 million times more massive than our Sun. That should help put the enormity of the situation we're in front of you into perspective. However, how do we manage to get this incredible picture of this unseen object? It wasn't simple, though. The black hole seems to be about the size of a donut on the Moon since it is situated around 27,000 light-years from Earth. The Event Horizon Telescope team had to build a virtual telescope the size of the entire world in order to take a picture of it. 8 current radio observatories on Earth were connected by the Event Horizon Telescope to create a single virtual telescope the size of the Earth. Then, they observed Sagittarius A** for several nights, gathering data for several hours at a stretch, much as when a camera has a long exposure period. The outcome is an amazing picture that offers compelling proof that the object in our galaxy's center is, in fact, a black hole. However, the image is much more than a nice picture. It represents a scientific discovery that has significantly advanced our knowledge of what occurs at the galactic core. In addition to providing fresh information about how these enormous black holes interact with their surrounds, the picture has validated a number of predictions made by Einstein under the General Theory of Relativity. However, a lot remains to be discovered about it. You see, while Sagittarius A is the nearest black hole to Earth, it wasn't the first one that we were able to thoroughly examine. Even before Sagittarius A* was seen, research was being done on another black hole, M87. M87, sometimes referred to as Messier 87, is an elliptical galaxy found in the Virgo constellation. A black hole, the first black hole to be directly photographed in 2019, is located in its nucleus. However, M87 was already a subject of curiosity for scientists before we even noticed its shadow. The strong radio radiation that M87 emits is one of the things that makes it such an interesting item. In fact, among the hundreds of galaxy systems that make up the Virgo cluster, it is the most potent known source of radio radiation. This suggested that the galaxy may contain extremely hot gas, which was verified when M87 was discovered to be a potent X-ray source as well. However, M87 is special not just because of its energy but also because of the manner in which it emits it. A bright gaseous jet extends from the galactic center. Synchrotron radiation, a kind of non-thermal radiation emitted by charged particles accelerated in magnetic fields and traveling at almost light speeds, is emitted by this jet. We can learn a great deal about the black hole's surroundings and internal operations from this radiation. When the Event Horizon Telescope captured photos of the galaxy's core in 2017 that revealed an asymmetric ring of radio emission encircling a black object, M87 grabbed headlines. The image was the first concrete proof of a black hole's existence, and that dark object was the black hole's shadow. With a mass 6.5 billion times that of the Sun, the black hole at the heart of M87 is not your typical black hole. Because the black hole is revolving, there is a brighter area on one side of the ring of radio emission around its shadow. The Doppler effect increases the emission of material on the black hole's side that is rotating toward Earth, giving the material a brighter appearance. Electrons are propelled to almost the speed of light by the gravitational energy produced by gas spiraling down into the black hole. It is believed that the brilliant gaseous jet coming from M87 represents radiation from this electron beam. These jets, which may travel hundreds of thousands of light-years, are some of the universe's brightest things. By heating up and releasing gas, they are believed to be essential in the development of galaxies, perhaps preventing more star formation. The black hole and surrounding disk of M87 have given scientists a once-in-a-lifetime chance to test Einstein's General Theory of Relativity, which describes how gravity behaves in the universe. That elevates things to a whole new level, especially when paired with what we've learned about Sagittarius A. The scientific community now has a wealth of opportunities to further their understanding of black holes with the discovery of 2 of them and a clear photograph of one. The fact that we can really examine 2 of them implies that we can finally compare 2 real black holes, even though we can't go as near to M87 as we can to Sagittarius A. This small information has the power to completely alter everything.
We believe that this is a significant finding. Finding things that we didn't expect or could not explain is the most fascinating part about this camera, this amazing instrument that we have deployed, because it forces us to reevaluate how we perceive the world. The primary cosmological hypothesis that describes how we came to be is the Big Bang Theory. However, the James Webb Space Telescope has found evidence that challenges this notion. According to Neil deGrasse Tyson, the Webb telescope discovered the black hole of the previous universe, which gave rise to our own. Perhaps the moment has come for us to acknowledge that the world has to be changed. But to what extent? Come along as we examine James Webb's discoveries, which are priceless to scientists. Is it possible that their measurements or their understanding of the Big Bang are off? C. The development of the gold hypothesis was among the most significant accomplishments of the previous century. According to the idea, the world as it is now evolved from a hotter, denser, and more uniform state. When fireballs, now known as the cosmic microwave background, were discovered in the 1960s, the theory, which was previously thought to be a credible explanation for the universe's expansion, became widely accepted. For almost 50 years, the Big Bang hypothesis has been the most reliable explanation for the beginning of the universe, the inflationary era that preceded it, and a certain condition of affairs. However, astrophysicists and scientists have long contested the Big Bang and the universe's expansion, and James Webb has discovered two additional links. Our picture of the cosmos may undergo a radical change as a result of his surprising discovery of early galaxies. Massive galaxies seen in the early cosmos by the James Webb Space Telescope raises questions about our current knowledge of the cosmic framework. The discovery does not quite fit into the available astronomical models. With barely 2 years of operation under its belt, the James Webb Space Telescope has already given us a peek into the early cosmos, a few 100 million years after the Big Bang. Many's perspectives were altered by the James Webb Space Telescope. Abruptly, we realized that the entire history of the universe could need to be redone. Astronomers have found 6 more massive galaxies than stars on Earth using the James Webb infrared detection technology. Our understanding of the genesis of galaxies may be altered if the sizes of these centers are verified. Based on information gathered by the James Webb Space Telescope, the research, which was published in the journal Nature, reveals that the Earth's age is just 3% of what it was 13.5 billion years ago. Then why are these galaxies so enigmatic? Galaxies began to resemble our Milky Way galaxy 13 billion years ago, an amazing development that occurred just 500 to 700 million years after the key event that heralded the formation of our planet. This object contains a star that is billions of times more massive than our Sun, and it may be a giant 100 billion times larger than our Sun. To put things in perspective, the stellar mass of the Milky Way is equivalent to 60 billion suns. In that sense, these galaxies dwarf the Milky Way in size. The University of Colorado Boulder's Erica Nelson, an astronomer who wrote the article, expressed amazement that a gap this size could form so swiftly. It defied logic to assume that galaxies with stars like our own would arise quickly in the early cosmos. Concurrently, the dust mound progressively grew in size. This view suggests that the issues facing the early world progressively came together. Nevertheless, these justifications fall short of explaining recent findings. How quickly these creatures grow is a subject that research director Evil addresses. The finding disproved the theory that the universe's massive galaxies required a very long time to form and called into question accepted scientific knowledge. Experts in astronomy refer to these objects as cosmic disruptors, informally, and they certainly live up to the moniker, appending and altering our conception of the universe's evolution. If this discovery is genuine, it might significantly alter our understanding of the early cosmos, according to astronomer Emma Chapman of the University of Nottingham in the United Kingdom, who was not involved in the research. It has been claimed that stars may have created more frequently than previously believed in the dark cosmic age, as evidenced by the finding of huge galaxies close to the Big Bang. However, scientists are cautioned before they begin to alter the course of cosmology. There's still a chance some of these objects might be concealed within a giant black hole. Gravity may have caused gas and dust in the image to collapse into what seems to be a star. The intricacy of the black hole's early development and growth is still unknown, according to a different scientist who was not engaged in the study. He said that rather than reflecting cosmology, the facts call for knowledge of the novel mechanism governing the formation and growth of the universe. Spectral images of items that reveal their age. The redshift of early universe galaxies indicates that their light is more stretched as it travels to Earth. The greater the redshift number, the more the light is stretched, signifying the galaxy's age and distance. Spectroscopy can indicate whether or not redshift candidate galaxies register as reddish galaxies from a recent cosmic epoch, as well as how ancient they appear to be. In order to observe, despite the outcome, astronomers claim that the detected quality constitutes an amazing occurrence, albeit further observations are required to confirm the discovery. There might be 100 times more stars from this cosmic age than previously thought. The University of Texas at Austin's Michael Bone, the author, views the issue differently even if the sample size has been halved. By publishing his findings in Nature Astronomy, he aimed to determine the percentage of regular matter that would require star formation in order to monitor the huge galaxies that James Webb had seen. He said, star formation used almost all of the available atoms. But according to Bone, achieving 100% efficiency with this method is almost unachievable. He said that by contrast, the current global percentage is only about 10%. This calculation's robustness originates from few assumptions. Does this imply that Vogelsberger's estimates are incorrect, even in spite of Bone's calculations? Lambda dismisses CDM. It was his final destination before choosing to replace it with another idea, he claimed, adding that no other thought was now impeding his powers. What additional reasons are there then? Approximately 500 million years after the Big Bang, Hilly Williams' team at the University of Minnesota made the stunning discovery of an early galaxy. Based on James Webb as well, the measurement device's resolution determined how blurry galaxies appear to be. Williams reported a star production rate 12 times greater than that of galaxies from a little later era. Though he assessed the likelihood of this star formation for bigger galaxies at similar redshifts, Williams confirmed that the galaxy was no more massive than the galaxies analyzed by Bohan. Its modest size, just 105 light-years in diameter, makes Bone cautious as well. It is smaller than the average galaxy. It was decided that the cluster would be worldwide. The lambda CDM can be modified as an additional solution to the problem in cosmological models. Dark energy's behavior appears to have changed shortly after the Big Bang, according to the early electron hypothesis. By making this change, it becomes consistent with the Hubble constant and keeps up with other observations. More issues in the early world are needed for this approach. According to Bone's calculations, there would be a threefold rise in the velocity of matter in the first galaxies, negating the necessity for ultra-low star formation of the same magnitude. Age differs significantly from the 13.7 billion estimate based on other metrics. The fact that part of the Milky Way's light can be mistaken for stars by astronomers is another explanation. Bohan considers the hypothesis that the light may be coming from the supermassive black hole's storage region to be excellent. Astronomers caution that while they have observed a few of these galaxies thus far, they may not be representative of the entire universe, as there are only perhaps 250,000 of them in the sky. A statistical analysis would settle the argument, according to Joel Leja of Penn State University, who was not engaged in the research. But the issue is, are these far-off galaxies really that? Distant, huge galaxies may be mimicked by neighboring low-mass galaxies, according to Peter Beruzzi of the University of Arizona, who was not involved in Bourne's research. More assessment is awaited on the ultimate outcome. Moreover, there are no spectroscopic data available for these galaxies, which would enable the determination of their actual distances and allow the hunt for black hole signs. After reviewing the material provided, Michael Bone concluded that a major issue will emerge in a few years or fewer. Let's examine some of the possibilities astronomers have proposed to explain this occurrence while we wait for this information. If we accept that supermassive black holes may have existed in the early cosmos, this riddle can be resolved. This idea is thought to help explain why big galaxies show up in telescopic views, according to astronomers. However, the challenge is to account for the large number of black holes that emerged in the early cosmos. Herein lies the relevance of the contentious Nobel laureate. Popular historians claim that everything that exists now and in the future, apart from around 14 billion years ago, exists in a separate dimension. All that is apparent to us is the result of this difference breaking down and creating. This is the most basic explanation of the Big Bang. But 13.7 billion years does not seem long enough, in the opinion of many scientists, to develop sophisticated structures like superclusters. To bolster his argument, an Oxford University physicist has questioned the conventional Big Bang theory. Based on the remnants of cosmic microwave background radiation, which was produced when Earth was just 300,000 years old, the scientist concluded that a vast circle rather than the Big Bang was the genesis. The cosmos enters a new phase with every event. There will be another Big Bang in the future, according to Sir Roger Penrose, the 2020 Physics Nobel Prize recipient, who is renowned for his contributions to mathematics and the study of black holes. Our universe has seen many Big Bangs. In the process of illustrating the depth of the material and finally crafting phrases that capture the sense of eternity, he also investigated the intricacy of black leather. Penrose maintained his skepticism and called the prize crazy when he accepted it. A second Big Bang and the creation of a new universe will result from the cosmos' expansion until all matter decays. It has already occurred and it will again. In what way, therefore, do scientists defend his conformal cyclic cosmology? By asserting to have found 6 hot spots, known as Hawking bits, each roughly 8 times the diameter of the Moon. Sir Roger Penrose refuted the widely accepted Big Bang hypothesis. Although these black holes are not like the 13.77 billion-year-old Earth of today, their discoveries suggest that they may exist. The name black hole comes from physicist Stephen Hawking, who proposed the theory that black holes generate electricity and eventually evaporate. The layer of nature that started before the real Big Bang is the only explanation for the unique, low-entropy state at the universe's creation in the inflation-based Big Bang scenario. Penrose proposed that as our universe expands to its ultimate limit and becomes empty, cold, and black, it would revert to a low-entropy condition. The existence of death black holes, which are relics from countless years ago, attests to this and might support Hawking's hypothesis. Evidence for an anomalous position of temperature in the cosmic microwave history was offered by Penrose in his 2020 paper published in the monthly notices of the Royal Astronomical Society. Roughly 10,000 simulations were used to analyze the data for these sites, which came from the Planck 70 GHz satellite. Due to black hole evaporation, Penrose discovered high temperatures in cosmic microwave background radiation in 2018. The gravitational waves responsible for the rings were previously observed when black holes collided throughout the cosmos. Black holes demolish stuff and leak energy. When the universe's expansion comes to a halt, they aid in lowering entropy. The leftover black holes will either condense or combine to form new ones. This leads to the appearance of the Big Bang scenario, which smooths out the present jagged geometry of space-time. Penrose's concept proposed that the next Big Bang will mark the end of the universe's expansion and its collapse into a finite cosmos, ushering in a new era. The common belief that variations in CMB temperature must be random is refuted by Penrose. He and Gurzadian discovered over 12 loops in NASA's WMAP satellite data, indicating the possibility that gravity did not exist in the past. If true, Penrose's coherent cyclic cosmology would do away with the necessity for a Big Bang leader by suggesting that the age of our universe may be indeterminate in the billions of years. If verified, this would represent a significant and demanding claim in the field of cosmology. Opponents argue that, as the world becomes older, everything should get smaller since it is difficult to combine an endless universe in one century with a little world in the next. Tell us if Penrose's idea makes sense or if, like so many others, it should be written off as a Big Bang theory. Thank you so much. Please like and subscribe.